Did you know that the two wires on a power cord like this repel when power is flowing? It's almost like they don't like each other. Well, I've set up a little experiment using these two dangling wires over here to demonstrate that for you. Our setup for the experiment is quite simple. I have an old high current battery charger over here, and its negative terminals are attached to this wire, and its positive terminals are attached to this wire. And the ends of the wire way over there are connected together. So when we turn on the battery charger, what it's going to do is send electricity, in this case electrons, down this wire in this direction. We'll put a minus sign here just so it's clear those are electrons. And they're going to go all the way to the end and then come back in the opposite direction on the other wire and go into the positive terminal over here. And what should happen is each of these wires will create a magnetic field based on Ampere's law, and that will affect the electrons flowing in the other wire and cause a force to be imparted on them based on the Lorentz equation. And, well, let's see what happens. Now watch the wires. And there they go. They move apart. Now, this is actually about 75 amps, so I can't leave it on too long or we'll see the wires melting. So why do the wires repel? Well, we've looked at Ampere's law before, and essentially what it says is if you have a wire with current flowing through it, you have a magnetic field going around that wire. There's another equation that we haven't looked at yet, and that's the Lorentz equation. And what it says is if we have an electric charge moving with a certain speed in a certain direction through a magnetic field, we generate a force that's at 90 degrees to both. And that's what this X means. It's the cross product, and it's the mathematical way of saying we use the right-hand rule. So here's our wire with the current coming back, and we have our B field going up. We have our current going in this direction, and so with the right-hand rule we get a force pushing the wire out away from the other wire. And of course the same thing works in the reverse, namely this wire gets pushed away from that one. What that also says is if we were to reverse the direction of this current, now that force would be in the other direction and the wires would attract. And we can demonstrate that. We'll tie the ends of our two wires together like that. And hook that to our battery charger. And I will take my extension cord and wind its ends together, and we'll hook it to the positive terminal, and I'm going to attach the other end of the extension cord to the distant end of our experiment. By the way, these vice grip pliers make really good temporary electrical connectors for experiments like this. So here you go. We've now got the two wires attached together at the far end to this extension cord, and we're just about ready to do the next experiment. The one thing we should do is correct our little drawing on the wood here. In this situation, we're now going to send electrons in the same direction down both of these wires and see what happens. Here goes. That was simple. In fact, these wires are actually better at demonstrating the attractive forces when current is going in the same direction, and that's because as they get closer, the forces get stronger. So we can actually adjust this just a little bit so they're a bit further apart and make this more obvious. So at this point you might be wondering, we've just done this experiment with DC. What happens if we apply AC to the wires in exactly the same configuration? Well, that's the quiz for this video. Think about it for a couple of seconds, and we'll try it. So for the AC experiment, what we'll do is use the good old AC arc welder that I've used in the past to provide us with the necessary AC current. We'll attach the business end of the welder to this end of the wire using our vice grip. Perfect. And we'll attach the extension cord, which goes to the distant end, to what would normally be the ground terminal of the welder. So here goes. Exactly the same thing happens. And I'll turn it off before we melt the wire. So why does it work just as well with AC? Well, with AC, first you have the current flowing in this direction, and we get a repulsive effect because the current is flowing in the same direction. And then the second half of the cycle, it's flowing in the other direction. Again, in both cases, the current is flowing in the same direction down the wires, and once again we have a repulsive effect. So it really makes no difference whether there's AC or DC. The bottom line is the wires that contain current flowing in the same direction tend to pull together like this, and the wires that have current flowing in the opposite direction tend to repel and move apart like that. And there's only one application that I can really think of this, and that is in the wires grounding lightning rods. Because what happens in a lightning rod is you have an incredibly large current flowing down all the strands of the wire in the lightning rod. And because of that, those wires are attractive and they push together. And what apparently happens is the wires that ground a lightning rod will actually get welded together in a really neat tight bundle if lightning hits. And that's apparently one way you can tell whether lightning has actually hit a lightning rod. So there you go. I hope you found this video interesting. In the next video, we're going to look at the actual fields around these wires. See you then.